Hello and welcome. We are going to look at question 1 of last year's paper, UACE chemistry. So, first question said, define the term standard electrode potential. For us to be able to define it, we need to have an idea on the setup that can be used to measure or determine the standard electrode potential of the given electrode. So, here we have our electrodes. We are having this copper electrode, and then we also have the platinum electrode. So in this setup, they have connected the copper electrode to the half cell of hydrogen half cell, and the solution of our copper to ions is 1 molar. So we shall define our standard electrode potential basing on some of these facts. So we shall say that this is the reduction electrode potential for an electrode measured with respect to the standard hydrogen electrode when the electrode is immersed in 1 molar solution of its ions at standard conditions. So we are saying it's the electrode potential. That means the potential difference that we shall have here for an electrode, in this case the electrode of interest. For example, here it's the copper electrode measured with respect to the standard hydrogen electrode. So because it is connected to the standard hydrogen electrode, what we are actually getting here is the potential difference, which we are referring to as our electrode potential for copper when the electrode is immersed in 1 molar solution of its ions. So the ions of copper are copper to ions, and the concentration is 1 molar at standard conditions. Because they have said define the term standard, the conditions also have to be standard. That is to say 298 Kelvin and a pressure of 1 atmosphere. So you could have said at 298 Kelvin and pressure of 1 atmosphere. Part B, they have given us the standard electrode potentials for some half cell reactions below. So you must have an idea on what this means. One thing to first identify is which kind of electrode potentials have they given us, oxidation or reduction. In most cases it's reduction, but you have to first clarify that. So remember, reduction is gain, which is our rig, while oxidation is loss, which is our oil. So because all our equations, electrons are on the left of the arrow, that means all these species are gaining electrons, and if they are doing so, this is a reduction equation, and therefore the electrode potentials given to us are standard reduction electrode potentials, which is a good thing because ideally that's what most of the scientists base on, reduction electrode potentials. So they're saying identify the strongest reducing agent and strongest oxidizing agent. So one thing to notice that species that are being reduced, these ones here being reduced, they are the oxidizing agents. The question is why? Of course, for you to be reduced, it means you are gaining electrons, but as you are gaining electrons, it means you are causing some other species to lose electrons. So if you are gaining electrons, you are causing some other species to lose electrons. So in this case, our cobalt ions, zinc ions, and the rest are strong. They are oxidizing agents because they are being reduced in the process. So how do we tell which one is the strong oxidizing agent? The one with the largest reduction electrode potentials. Largest, I mean most positive. So we shall look for the most positive. Which of these 4 has the most positive reduction electrode potentials? So in this case we shall find it is manganate 7. So this is the most oxidizing agent. However, On our right of the equations, we have these other ones which are reducing agents. Why are they reducing agents? Because they are being oxidized. They are losing electrons to form what is on the left. So as they lose electrons, they are being oxidized. But for it to oxidize and lose electrons, you are causing other species to be reduced, and therefore they are reducing agents. So which one is the most or strongest reducing agent? The one that will have the most positive if we reverse the equations. But before we do so, for now we shall have to base on the least positive, which will be this one here. But let's reverse them because it's easier to see the most spontaneous if we reverse these equations. If we reverse the equations, meaning we are moving from right to left, we also have to change the sign of our electrode potential. So we shall have positive 0.28, positive 0.76, negative 1.36, and negative 1.52. So the most positive is this one, which corresponds to zinc. So zinc is the strongest reducing agent, while our manganate 7 iron is the strongest oxidizing agent. Don't forget the word iron. Roman to write the cell notation of the cell constructed by combining these two half cells. Now to come up with the cell notation, we need to first come up with the reactions at the different electrodes. So we have the anode, we also have the cathode. Remember, the anode is where oxidation occurs. So here we must have oxidation half equation, while this side we must have reduction half equation. So ideally it's simpler for me to first start with reduction by picking which of these two half cells, the one for cobalt and the one for zinc, has the highest positive reduction electrode potential. So I'll come and look at cobalt and also look at zinc. Which one is the most positive? Because we said the most positive means the forward reaction is spontaneous. So the one that is most positive or less negative will be the most spontaneous. So on these two, the most positive is cobalt. So in this case, cobalt is going to gain electrons, and therefore we shall have cobalt 2 ions aqueous, picking 2 electrons because reduction is gained, and then becoming cobalt solid. So these 2 electrons must come from the less positive, which will be our zinc. So in this case we are going to have a backward reaction occurring at the anode, so meaning that zinc will lose 2 electrons to form zinc 2 ions aqueous and the 2 electrons. So with this in mind, we can now come up with our cell notation. Remember, when writing the cell notation, there are some rules to follow. So we are going to start with the element that undergoes, the half cell that undergoes oxidation. So we are going to start with our anode. So we shall start with zinc, separate the phase from zinc 2 ions, then cobalt 2 ions, and then cobalt. So we shall have the following expression. So zinc, the state is solid. We shall put here a line that can separate the phase between solid and aqueous, zinc 2 ions. Then we shall put here parallel lines to show our salt bridge, followed by copper 2 ions aqueous. Separate the phase of aqueous from that of solid, and then we have our cobalt. So here we have to try and always remember that the species that has the highest or the higher oxidation state will be next to our salt bridge. That's why we are saying that we are having zinc 2 ions and then cobalt 2 ions next to the salt bridge. So simply put, zinc loses its electrons to become zinc ions. Cobalt 2 ions will pick the 2 electrons to become cobalt, and that becomes the cell notation. Write the equation for the overall cell reaction for the cell in B Roman 2. So for this cell, we are going to combine this equation 1 and equation 2 to come up with overall. So we shall have zinc reacts with copper 2 ions to form zinc 2 ions and cobalt solid. The electrons will cancel out if you add equation 1 plus equation 2. So we shall come up with something like that. Don't forget state symbols in each of these cases, and try and write the right element symbols. So calculate the e.m.f of the cell in B, Roman 2. So to calculate the e.m.f of this cell, cobalt and zinc half cells combined, we have to first go back to our reduction electrode potentials and identify which of these two is the most positive. Or we shall simply use the formula that the e.m.f of the cell is given by the e.m.f of the half cell on the right hand side, or the electrode potential of the half cell on the right hand side minus that on the left hand side. So the right hand side we are having cobalt, so we shall get most positive or least negative, which is minus 0.28, then minus 0.76, and then we shall get the actual e.m.f. So even if we flipped the equation here, please don't change the sign on zinc. Maintain the signs as they were given, or maintain the signs of the reduction electrode potentials. That's all I had for you. Have a nice day. If it's morning, stay safe.